So the next two sections are dealing with factoring polynomials. And our goal is to really be able to factor any polynomial. We know we can factor quadratics if they have nice numbers. We've seen a little factoring. We had an x squared minus 2 that we factored with some square roots. But now we're going to make it a little bit more interesting, and it's really going to get interesting in the next section when we introduce complex numbers to all of this. So let's get started. We're going to start with just redefining the division algorithm and reminding ourselves what that is, because we're going to use some division to help us with these. So if f of x and g of x are polynomial functions and g of x is a function whose degree is greater than 0, then there are unique polynomial functions q of x and r of x, such that if we take f of x and we divide it by g of x, there's always going to be a quotient, and there could be a remainder. Depends on if this is actually a factor of f of x. So we're going to get the quotient, and we could rewrite this as the quotient plus the remainder divided by g of x. Or if we were to multiply both sides by that g of x, we could rewrite it as the quotient times the divisor plus the remainder. The remainder theorem is a theorem we can use to help us determine if there's going to be a remainder. So for a polynomial f of x, if we take f of x and we divide it by x minus c, then the remainder is really the same number as whatever f of c would be. So we could just plug that number into that polynomial, and that would tell us what the remainder is. Now, in this case, the remainder is always going to be a number here because we're dividing by a linear term. So how do we know if we have a factor? Well, we're going to have a factor if that remainder is 0. So the factor theorem is actually two separate statements. If f of c is equal to 0, which means that the remainder is 0, then that means that x minus c is a factor of f of x. And if x minus c is a factor of f of x, then that means that that remainder would have to be 0. This is an if and only if statement, which means it works forwards and it works backwards. So let's use an example, and we're going to build up all of this gradually. I want to really start with that remainder theorem. So it says, use the remainder theorem to find the remainder when f of x is divided by x minus c. So if we were to plug in our c value here, now notice the c is the number after the minus here. So we could rewrite this as x minus negative 3. There's our c. If we plug negative 3 in for x, so we're going to have 3 times negative 3 to the 6 plus 82 times negative 3 cubed plus 27. We're going to get 0. So that tells us the remainder is 0. Now, we would get the same thing if we did long division or synthetic division. So if we took x plus 3 and we divided that into 3x to the 6 plus 82x cubed plus 27. I'm going to fill in those zeros here. This is going to be fun. So let's review long division. We ask ourselves, how many times will x go into that 3x to the 6? Well, it goes 3x to the 5th times. multiply through. So we have 3x to the 6th plus 9x to the 5th. Subtract. So those cancel. 0 minus 9 would be negative 9x to the 5th. And then we bring everything else down. So then we do the same process. How many times does x go into negative 9x to the 5th? It goes negative 9x to the 4th times. Multiply through. Negative 9x to the 5th. Minus 27x to the 4th. Subtract. X to the 5th cancel, and we have a positive 27x to the 4th. So you can see how tedious this is going to be. X goes in the 27x to the 4th. 27x cubed times. Multiply through. 27 times 3 is 81. We're going to subtract. That cancels. 82 minus 81 is 1x cubed. X goes into x cubed, x squared times. Multiply through. So we have minus 3x squared. Divide again. Minus 3x. Multiply through. Minus 3x squared. Minus 9x. Subtract. So that's 9x plus 27. And then we would have a 9 here. So 9x plus 27. Subtract. And then everything cancels, so we get 0. So we did all of that just to get that remainder of 0. So that's a pretty tedious process to go through to do that when we can use the remainder theorem. And the remainder theorem tells us that if we plug in that C value, whatever we get out is going to be the remainder. And we saw that in this particular example. So let's use the remainder theorem on the next one. We want to plug in and find out, is x minus 2 a factor? Well, in the last one, since we got a 0, then we would say x plus 3 is a factor. Which means that if I take x plus 3 and I multiply it by this quotient up here, I will get that dividend that in the inside of the little box there. I will get this guy back. So that's what that division algorithm is saying, is that you can rewrite this f of x in terms of factors and quotients and remainders. So now let's go on to 11. We want to find the remainder. Well, our C value here is going to be 2. So if we plug 2 into this function, when I did it, I got 8. So here's what that's telling us. 8 is not 0, which means that x minus 2 is not a factor. So if we went through that division process, we would get 8 as the remainder. It would show up here once we went through the division. Now, before we move on, I do want to do the division on that one so you can see that this works. But I want to do synthetic division. Synthetic division will make our life a little bit easier in this particular section. So in this example, we had x minus 2, and we were going into 4x cubed minus 3x squared minus 8x minus 4. So if we did long division, we would set it up that way. Synthetic division is nicer. So if we take x minus 2 and we set it equal to 0, our c value was 2. So that was c. That 2 goes in a box. Beside the box, we are listing the coefficients of that polynomial. So here's how synthetic division works. You bring the first term down. Then we're going to multiply and put that product in the next space. And then we add. Then we're going to multiply, put it in the next space, and then add down the column. And then we're going to multiply, put it in the next space, and then we're going to add. Guys, from the last page, this was a plus 4. So that should be a plus 4 here. So I'm going to clean that up. So we're going to multiply and then get here. So we get 4. If we add down that column, we're going to get an 8. Now, that last term is always the remainder. So we got a remainder of 8 using the remainder theorem. We verified it using synthetic division. These are the coefficients of the quotient. So this would say 4x squared plus 5x plus 2 with a remainder of 8. If we do that other one from number 15, we were looking at 3x to the 6th plus 82x cubed plus 27. We were dividing in x plus 3. So you got to find your c value. It's easier, I think, if you set it equal to 0 and then you solve it. There's your c. That's your box number. Now we're going to list the coefficients. So we have a 3x to the 6th. We had a 0x to the 5th, a 0x to the 4th, 82x cubed, 0x squared, 0x, and 27. Bringing the first one down, we're going to multiply, add down the column, multiply, add down the column, multiply, add down the column, multiply, add, multiply, add, multiply, and add. So we get that remainder is 0. And that's exactly what we got with long division and with the remainder theorem. And this is what's left. This is always going to be 1 degree less than what you started with because you're dividing by a linear. Synthetic only works when you divide by a linear term. So we started with a 6th degree polynomial. This ends up being a 5th degree. So, going back to our problem, we sidetracked there with synthetic division. We found that this is not a factor because the remainder is not 0. So remember, our goal is to break these down. We've got to have a starting place. How do we even know where to start on these? Well, that's where the rational zeros theorem comes in. So the rational zeros theorem says that we're going to find a list of possible rational zeros. And I call it my PQ list. So we have this polynomial here. And P is going to be factors of that number that's on the end here. Q is going to be factors of the leading coefficient. So then our P over Q is going to be the ratio of those. And if there is a rational list, rational means it is an integer divided by an integer, then it is guaranteed to be in that list. Now, it's possible we may not have any rational zeros, but if there's one, it will always be in this list. So the number of real zeros cannot be more than the degree. So if we have a degree 2 polynomial, we could have 2 real zeros. If we have a degree 3, we could have 3 real zeros. So what are the steps for finding the real zeros of a polynomial? First, it's really nice if you know what's the maximum number you're looking for. Second, you want to use that rational zeros theorem to find the possible list of rational zeros. And then we're going to use the remainder and factor theorems. We're going to start plugging those in. And if we get one that gives us 0, then that's great, because then we know we have a factor. So we're really just looking for the ones that give us 0. So then we can use synthetic or long division to help us solve the problem. Now, sometimes we'll get irrational zeros. Irrational means that we have square roots that are not very nice square roots in them. So, let's look at a few examples. We want to find the real zeros for number 39. So we have f of x is equal to x cubed plus 2x squared minus 5x minus 6. So our first step is to look at p's and q's. So p's are going to be factors of negative 6. Well, what numbers can I multiply together to get a negative 6? Well, I could use a 1 or I could use a 6. Now, I'm using plus and minuses here because it could be a positive 1 and a negative 6, or it could be a negative 1 and a positive 6. So there's lots of different options. We want to take into account every possible option. We could also have a 2 and a 3. So there's all of our possibilities for P. Q are going to be factors of that leading coefficient 1. And the only way I can get 1 is if I multiply a positive 1 times a positive 1, or a negative 1 times a negative 1. So if I take P over Q, if I take every number here and I divide it by 1, 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 1 is 3, 6 divided by 1 is 6. So if there is a nice number that's a 0, it is guaranteed to be in that list. So now, this is where we're going to use our calculator. We're going to start plugging these numbers in here. And this is where you may want to use that table set feature. I'm not going to be able to pull my calculator up right now because it would be sideways. So, we're going to plug these numbers in. So let's plug 1 in. If we plug 1 into that equation, what do we get out? Okay, when I plug a 1 in, I get negative 8. So we know that 1 is not a root, so that's not going to help us. Now let's plug in negative 1. Okay, if we plug negative 1 in, I got a 0. So here's what that means. That means x equals negative 1 is a root. And if we have the root, we have the factor just by moving that number over. So x plus 1 is the factor. So we have one factor. Now we could stop and do synthetic division, but let's check them all because it's really easy just to type these into the calculator. So let's plug in 2. If we plug in 2, we also get 0. So that means that x equals 2 is a root. So x minus 2, if we move that 2 over, is the factor. Now, since this is degree 3, we could have 3. So let's keep going. Let's see if the other one's in here. Let's do negative 2. Negative 2 gives us a 4, so that one doesn't work. 3 gives us 24, so that one doesn't work. But negative 3 gives us 0. That means x minus 3, x equals negative 3 is a root. So x plus 3 is a factor. So remember, we could have 3 factors, and we found 3, so there's no reason for us to check the 6 and the negative 6. So this guy is going to factor into these 3 things multiplied together. So there's our final answer for that one. Now let's do 56. We have f of x is equal to 4x to the 5th plus 12x to the 4th minus x minus 3. Let's do our PQ stuff. P is going to be factors of that negative 3, so we can multiply 1s and 3s together to get that. Q's factors of the leading coefficient 4, so we can multiply together 1 and 4, or we can multiply together 2's. So our PQ list is going to take every P and divide it by every Q. So we're going to have 1 divided by 1, 1 divided by 2, 1 divided by 4, 3 divided by 1, 3 divided by 2, and 3 divided by 4. So we have quite a few here. Now let's see which ones work. So we're going to use our calculator. Type this guy into your calculator. So if we plug 1 in, we get 44, so that doesn't work. If we plug in negative 1, we get negative 50, that doesn't work. If we plug in 1/2, I got negative 3.4, so that doesn't work. What about negative 1/2? Well, negative 1/2 is negative 0.26. Negative 2.6. Sorry, that doesn't work. Let's try 1/4. Nope. Negative 1/4. Nope. Okay, I think I had something typed in incorrectly in my calculator. So let's go back to this. If I plug 1 in, I got a 12. If I plug negative 1 in, I get 6. So neither of those work. If I plug in 1/2, that doesn't work because I don't get 0. If I plug in negative 1/2, it won't work. 1/4 and negative 1/4, those don't work either. I get decimals for those. If I plug in a 3, I got 1938, so that doesn't work. But if I plug in a negative 3, I get 0. Whew. We finally got one. 1.5 doesn't work. Negative 3 halves or negative 1.5 doesn't work. And the other ones don't work. They all give me decimals. So it looks like the only starting point we have comes from here, where f of negative 3 is 0. So here's what we know. F of negative 3 is 0. So x equals negative 3 is a root. X minus 3 is a factor. X plus 3 is a factor. We want to add this to the other side. We want everything on the same side. So let's do synthetic division. We don't know a whole lot here. We have 4x to the 5th, 12x to the 4th, 0x cubed, 0x squared, minus x minus 3. If we bring that 4 down, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. So there's our remainder. We already knew that remainder was going to be 0. Remember, this is 1 degree less. So we started with a 5th degree, so this would be 4x to the 4th, 0x cubed, 0x squared, 0x minus 1. So here's what we know. I'll write it over here. Our f of x was originally 4x to the 5th plus 12x to the 4th minus x minus 3. Now we know this factors into x plus 3, right, times this guy. And we can actually bring this guy down because that's a difference of squares. So there's our factored form. The last thing in this section is the intermediate value theorem. And the intermediate value theorem is an existence theorem. So it shows you something exists but doesn't tell you how to find it. So let's look at an example. We have this function and we're looking on an interval from negative 1 to 1. We are asking the question, is there an x-intercept on that interval? That's what we're asking. So, intermediate value theorem. Here's how it works. We're going to plug in those endpoints for that intercept. For that interval. So, if we plug in a negative 1 into that function, we get a negative 6. If we plug 0 in, we get a 2. So, we have a polynomial. We know it's continuous. That's part of the criteria here. And here's what's going on. We actually found 2 points on this graph. At negative 1, we're down at negative 6. And then at 0, we're at 2. Well, if this is continuous, I have to be able to connect those dots. And the only way I can connect those dots is if I cross that x-axis. So that means that yes, there is an x-intercept on that interval. So the intermediate value theorem guarantees us there's one that exists, but it doesn't tell us how to find it. So to find it, we're going to have to use that PQ stuff. So let's do that. P is going to be factors of that 2. So factors of 2 are 1 and 2. Q is going to be factors of the leading coefficient 1, which is 1. So our P over Q list, I take each of these, divide by the 1. 1 divided by 1 is 1. 2 divided by 1 is 2. So this is where we would see if one of these numbers works. So let's try it. If we plug in a 1 and a negative 1 and a 2 and a negative 2, do we have a factor here? And it's possible we may not have a factor. So we're going to type that equation into our calculator. And we're going to start plugging those numbers in. So if we plug in a 1, I got 10. So we don't have a factor there because the remainder when we divide would be 10. Negative 1 gives us a negative 6. That doesn't work. 2 gives us 78. And negative 2 gives us negative 50. So that doesn't work. So there is just not a nice value here. And what that means is that this x-intercept must be irrational. So this is where we would use some kind of technology to help us solve it. Other classes talk about something called root finding algorithms, and we would use a root finding algorithm to solve it. But I'm going to use, you can use your calculator in the zero feature. If I try to turn my calculator on right now, it would be sideways, so I'm going to use Desmos. So there's our graph. Now, I'm going to zoom in on this, if it lets me. So there's our graph. We want to know, is there an x-intercept between 1 and 2? So here's x equals negative 2. Here's x equals negative 1. Sorry, x-intercept between negative 1 and 0. You can see it's crossing that axis right there. And in fact, I just hit it. So there's our x-intercept. This is rounded to 3 decimal places. So the intermediate value theorem guarantees us an x-intercept. To find it, we have to use other means to find it because it doesn't tell us how to find it. So in this case, our x-intercept is negative 0.605.